Okay, so let's take a look at putting some of this to work on the first of today's lecture worksheets. So this is 12.1 lecture worksheets. And in the video, you had a quick review of the chemical, what a chemical name is, a chemical formula, a structural formula, and a condensed structural formula, and also the line angle drawings. So we're going to be working with all of those in this upcoming module. And what you have right here is talking about some different isomers that have the same chemical formula. So the chemical formula shows what atoms and how many. So for instance, this chemical formula here, this is 1, 2, 3, 4, 5 carbons and 12 hydrogens. So that's all carbons with all single bonds. You can always use the alkane chemical formula. So the alkanes are all single bonds and only carbon and hydrogens. And you can calculate that using Cn, and then the number of hydrogens is Hn plus 2. 2n plus 2. That's the number of hydrogens. So that's how I got C5H12 for this molecule. Well, we can draw different structures. So the structural formula, that's the structure that shows the atoms and how they're bonded. So it's not a formula like a math formula, and neither is the chemical formula, but that the molecule here, we can draw the straight chain isomer, because this is right here is a branch. So this is called a branch. It's off the main chain, which has 1, 2, 3, 4 carbons. So we can draw a straight chain version of this that does not branch. So that basically means 5 carbons, 1, 2, 3, 4, 5 carbons. And those 5 carbons all have single bonds, and they all have to have 4 bonds coming out of a carbon. And those bonds that are not attached to other carbons are going to be to hydrogens. So make sure every carbon has 4 bonds, and that those bonds that are not attached to carbons are attached to hydrogens. So this is called the straight chain isomer, when you just have the carbons without any branch. Okay, so this is the straight chain isomer here. So let's show this as the line angle drawing. So the line angle drawing is going to be 1, 2, 3, 4, 5 carbons. This is called the line angle drawing. You don't have to do any symbols if you have carbons. The carbons are at the end of the line or at any branch. At the end of the line or any vertex. And this version of the line angle drawing is 1, 2, 3, 4 carbons. So let's draw this 1, 2, 3, 4 carbons. And then there's a branch also coming off of this carbon number 3 in the chain. So there's 1, 2, 3, 4, 5 total. Okay. Now this would be equivalent if I flipped it. So if I flip it like this would be 1, 2, 3, 4 carbons, and then a branch. Okay, so this is the same. This one is the same as this one, and they are all versions of this branched isomer. Okay, and so the another version of this that we can draw, let's see, we can do 4 carbons. We can do 3 carbons, 1, 2, 3, 4, and then 5. 1, 2, 3, 4, 5 carbons. So this is another version. And then drawing this out, this would look like this. This is a carbon with 4 carbons attached to it. And then each of those carbons has to have enough hydrogens. So every carbon has to have 4 lines coming out of it. And if it's not bonded to carbon, it's going to be to other hydrogens. Okay, so this is another version. So let's count. This is number 1. This is version number 1. This is version number 2. And the straight chain is version number 3. I think that's all I can get out of that. So I've got three other, these are all isomers in which you can draw different line angle drawings or different structures with the same chemical formula. They all are the same chemical formula, which is C5H12. Go ahead and count these 1, 2, 3, 4, 5, and then there's 3, 6, 9, 12 hydrogens. There's 1, 2, 3, 4, 5, and then there's 12 hydrogens in there. Same thing there. As long as they're all single bonds and all carbons and hydrogens, you're always going to get the same number calculation of hydrogens. When you throw in double bonds or triple bonds, then you're going to get different numbers of hydrogens. When you have a ring structure, then you're going to have different numbers of hydrogens. But when you have all single bonds, only carbon and hydrogen, it doesn't matter if there's a branch in there, you'll still have the same number of hydrogens. Okay, so let's focus on this carbon skeleton and first write its chemical formula. So the chemical formula, we need to count how many carbons there are. 1, 2, 3, 4, 5, 6, 7, 8 carbons. So this is C8. And then the number of hydrogens, we can use that formula where the number of hydrogens is 2 times the number of carbons plus 2. So this would be 2 times 8 plus 2, which is going to be 18. C8H18, H18, which would be how many hydrogens if you added hydrogens to all of those. So this is the carbon skeleton with, there's a few branches going on here. Here's 1, 2, and 3. So the straight chain isomer of this would be having just 8 carbons. 1, 2, 3, 4, 5, 6, 7, 8. That would be the straight chain isomer. Okay, you could add hydrogens to all of that, but we're just focusing on the various carbon skeletons here. So these are other carbon skeletons, and which ones are possible isomers? So they first need to have 8 carbons in order to be a possible isomer, because it has to have the same chemical formula, which is C8H18. As long as there's 8 carbons and they're all single bonds, it'll have the same chemical formula. But we need to rule out any that don't have 8 carbons. So let's go ahead and count all of these. So this has 1, 2, 3, 4, 5, 6, 7, 8. This is a possibility. 1, 2, 3, 4, 5, 6, 7. This has 7 carbons, so this cannot be an isomer. This has 1, 2, 3, 4, 5, 6, 7. This also has 7 carbons, so this one cannot be an isomer. And this has 1, 2, 3, 4, 5, 6, 7, 8. Okay, so these two are possible isomers. We haven't decided yet, because one thing we got to look at is that you cannot have branching if the carbon branch is at the end of the molecule. Okay, so if it's at the end of the chain, it doesn't count as a branch. If it's at the end of a chain, this is an example here. I'll change this to red. This is a branch at the end of the chain. At the end of the chain, it's not actually a branch. Just like a branch on a tree, it has to come out from the middle. If it's at the end, it actually just means that it can be considered part of the same straight chain. Okay, so this is something that is a rotation around that carbon. This carbon can either be flipped up here or flipped down there. So this is the same thing is true here of this carbon that's at this end of this chain. This can be flipped up and be represented like that. So when you draw this with this, the possibilities, ruling out any branches that are at the ends, then that makes this exactly the same. This is exactly the same. So you've got a carbon with 2 bonds coming out of it, and then a branch right next to it. So this is exactly the same because of that carbon here being flipped up. So this, I'll highlight this in green. This is exactly the same as this one. Okay. And everything else is exactly the same. The 2 carbons bonded to that carbon, and then that branch right there. So there's exactly the same. So that's one isomer. So this is one possible isomer. But this is different. So this next one, I'll circle this in red. This is different. That's because you have a 1, 2, 3, 4, 5, it looks like. And then the second carbon has the branch with one carbon, and then the middle carbon has two carbons on it. So that's what's going on with this one. So this is a different version. So this is a different isomer from this isomer number 1. So this is showing two possible isomers. The isomer being different structures, but the same exact chemical formula, and the same chemical formula is this chemical formula C8H18. Because if you add hydrogens to all those carbons, you'll find that they're exactly the same. Okay. So when we're talking about the structural formula, remember that's the structure, and the line angle drawing, that's showing the short version for each isomer of hexane. Let's start with what is hexane. So hexane has the beginning part of the name hex, which means 6. ANE is the end part of the name, which is the 6 carbons of the alkane family. And alkane, remember, means only carbons and hydrogens and all single bonds. So that means when you're drawing 6 carbons with all single bonds, 1, 2, 3, 4, 5, 6, this would be the straight chain version. You just draw all those carbons straight across. Okay, so then we're going to add all of those, making sure that every carbon has 4 bonds and each of these lines connects to a hydrogen. So add hydrogens, and this would be the straight chain version of hexane. Okay, so this is C6 and H14 when you count all those hydrogens. Now, the line angle drawing of this straight chain is basically converting each carbon to a dot. 1, 2, 3, 4, 5, 6. So the ends of the line, and then every vertex where 2 lines meet, that's representing a carbon. And then all the hydrogens are implied in there. Okay, so that's the line angle drawing. So let's see if we can come up some different isomers where basically you still need to have 6 carbons, but you want to have some branching. So from branching, let's start with having 5 in the straight chain. 1, 2, 3, 4, 5, and then here's a branch. Okay, so that branch is coming off this first carbon. Now, if I flip this, the mirror image of this would be 1, 2, 3, 4, 5. The mirror image would be exactly the same. So this is one possible isomer, those two together. Okay, so that's one possible different structure. That's what an isomer is. Another possible isomer is taking this 1, 2, 3, 4, and then having 2 branches, 1, 2. And then this could also be flipped for the mirror image. And it would be exactly the same, just the mirror image. So this is another possible isomer. Okay, and then let's try another possible isomer would be 1, 2, 3, and then have 2 branches off of 1 carbon. And then you'd still have to have 1 more carbon there. So this is another different where you could also draw the mirror image, 1, 2, 3, 4, like that. Okay. And so this is a third possible isomer. So I've got, let's see, I think I've got all the possibilities here. I think there's one more I can do. 1, 2, 3, 4, 5. Nope, that's the same as that one. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Let's make sure that's not the same. And this is another one where I've got a base of 4 in the straight chain, and then I'm adding 2 more. So this is a branch coming off here. So this would be the mirror image of this. Okay, so this is a fourth possible isomer. Now, my point in all this is, for one, first of all, understanding the line angle drawings. And second, understanding that branching. So this is called a branch when you have a carbon off the main chain. it's called a branch. And branching allows for different structures with the same exact atoms. But when you have a different three-dimensional structure, that allows for a different function. And so that opens up a lot of possibilities in biochemistry. When you have a shape that's different, then you can have a totally different function. It can do something different in the body if the shape is different. Okay, and so that's the main reason. I know this can get kind of complicated with the different isomers, but the main thing is understanding that there are isomers. Those are different structures with the same chemical formula. Okay. So this next page in the lecture worksheets is a review that we're going to look at just briefly before jumping into the worksheet. But this is the names of those alkanes are here. They start with the mnemonic mother eats peanut butter, M, E, P, and B, and then continuing on to pent, hex, hept, oct, non, and dec. And those, the beginning part of the name, the prefix tells you how many carbons there are. And so we could write the chemical formula. This would be C1H4 for methane, or ethane is C2H6. Propane is C3H8. And then continuing on, you could continue on with all of these. The general chemical formula is CnH2n plus 2 when you're talking about an alkane to calculate the number of hydrogens. Okay, we're also going to add in looking at more of these condensed structural formulas that shows what's bonded at each atom, at each carbon grouping. Okay, and so we're also going to show the line angle drawings or work with line angle drawings. So when you have methane, that's just one carbon. The line angle drawing is actually not a line. So we'll build some of these line angle drawings over here. But for methane, you only have to have a dot. And for ethane, you're only going to have two carbons. So it's two dots connected with a line. But once you actually have three carbons, then you got to move into the zigzag, because you cannot just have a straight line with three dots. It becomes too confusing. So this would be the line angle drawing for propane, would be three dots, and you start to make it zigzag. But it's not actually zigzag. It is simply to understand the lines and having those angles. But when you fill it in as the space filling model or the molecular view, it's just a thick line with all those atoms. So this is, the next one is butane, C4H10. So there's 1, 2, 3, 4. And then you just keep going, 1, 2, 3, 4, 5 for pentane, 1, 2, 3, 4, 5, 6 for hexane. And you can see the benefit of the line angle drawing. You don't have to have any of those carbons or hydrogens. So heptane 1, 2, 3, 4, 5, 6, 7. Octane 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8. Nonane 1, 2, 3, 4, 5, 6, 7, 8, 9. And then decane 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you now are looking at not a bunch of zigzag lines, but you are looking at carbons and hydrogens. And that's what the condensed structural formulas show you, what's bonded to each carbon. Okay, we're going to get to this next worksheet, which is representations of organic molecules, but let's take our 10-minute break first.
I'm sorry, Professor, can you just go up for a few seconds? Thank you.
This is a review over all those different representations of these organic molecules that you'll find in organic chemistry. So remember, organic chemistry, those are just carbon-containing compounds. So not the same as organic food, which is grown without synthetic pesticides or fertilizers. So there's a difference. Organic chemistry, basically the organic molecules, is a lot wider definition. So when you are representing an organic compound, there are these different ways talking about the chemical name, the chemical formula, which shows what atoms and how many. We already looked at, for example, methane. showing what atoms and how many would be CH4. And then the structural formula shows the atoms and how they're bonded. So this would be a carbon with 4 hydrogens. The condensed structural formula just shows what's bonded to each carbon atom. And that would be CH4 in this example. The ball and stick model is getting into the 3-dimensional. And this Vesper shape would be a central atom carbon with 4 bonds to it. And that would be the tetrahedral shape. So let's draw that tetrahedral shape, which would be the carbon, a hydrogen at the top, a hydrogen at the side. And then remember, this tetrahedral has 1 hydrogen coming, or 1 atom coming out with the thicker line, and then 1 going in the back of the plane, and that's the dashed line. Now the space filling model, that's the more realistic view, and that is when you have the colors. I'm going to add in the colors. So this is carbon is typically shown as the black, and then hydrogens are as white. And so this would be with the, going back here, having 4 hydrogens, and they are all smushed together. Those are covalently bonded atoms when the atoms are smushed together like that. And then finally, when you have the line angle drawing, that's the simplified version with the zigzag line, the vertices, or when you just have a dot, that is 1 carbon. Okay, so let's see if we can do some of these when you are given different versions, where you're given different name, given the name. So we covered methane, got all that up there. Let's look at butane though. So butane has the prefix but. That is the B in the alkane family. So the ANE means alkene family. And those are the hydrocarbons with all single bonds. And so the but prefix means that there are 4 carbons. So this is the chemical formula starts with a C4. And for the alkanes, we're looking at the chemical formula CnH2n plus 2. So that would be 4 times 2 plus 2, or 10 hydrogens. Now, what's going to be the structure is going to give us this 4 carbons, 1, 2, 3, 4 carbons all in a straight line with all single bonds. So that's just make sure it's single. And then every carbon has to have 4 bonds. So every carbon should have 4 bonds or 4 lines coming out of it. So let's make those bonds 1, 2, 3 are added to the one on the left. And then 1, 2 to each of those center carbons, because each carbon in the center has 2 bonds to other carbons. And then this last carbon on the right, you're going to need to add 3 hydrogens. Okay, so this is going to be the normal version, or the straight chain is called the normal version. And that's why it has N-butane, okay, as the name. So now the condensed structural formula shows what's bonded at each carbon grouping. So from the structural formula, you can actually convert this to the condensed structural formula fairly easily. So this is going to be CH3 is this first group. Actually, let me underline this with different colors. So this first group is CH3. The second group is a carbon with 2 hydrogens. So that's going to be CH2. And then this third group is another CH2. Okay, so that's this third group is another carbon with 2 hydrogens. And then this fourth group is a carbon with 3 hydrogens. So that's going to be a CH3. Okay, the line angle drawing, converting that to the line angle drawing is just taking each carbon and making it a dot and then connecting the dots. So this is 1, 2, 3, 4 carbons, and that would be the CH3, CH2, CH2, CH3. Okay. When we're talking about this next isobutane, the chemical name has iso. So iso means it's an isomer of butane. So if it's an isomer, the isomer definition is the same chemical formula. So it has to have the same chemical formula. So it's still going to be C4H10. But the structure is different. So that's the same chemical formula, but a different structure or different structural formula. So looking at this next structural formula, we have to make it different. The different structural formula is due to bonding with a branch. So a different structure can be 3 carbons as the main chain, and then having a branch. Now, your choice is really only to have a branch off the middle carbon. There's only 4 carbons in this whole molecule, and you can never have a branch off any of the end carbons, because a branch off the end means it's just flipped up or down. So this can be a branch going up, or it can be written as a branch going down, and it's the same thing. Okay, it's just the mirror image when you put the mirror 180 up, down. So this would be the structural formula will include all of those hydrogens to make sure that every carbon has 4 bonds sticking out of it. So that is going to be exactly the same as this one. I'm going to make this an equal sign. Give myself a little more space here. Okay, so these are the same. And every carbon is going to have enough hydrogens, and then you will find when you add all those up, it's still 4 carbons and 10 hydrogens. So the condensed structural formula shows what's bonded to each carbon. And so just looking at this, you start with a CH3, and then it's bonded to a carbon that has the center carbon right here. The center carbon has a hydrogen, so it's a CH. And then there's a branch off of it. So I'm going to just highlight the branch, this branch right here in red. So this is a CH3 branch. And the way you indicate a branch in the condensed structural formula is by putting it into parentheses. So on that CH, so this CH is right here, the CH, I'm going to put in parentheses now, CH3. That's how I indicate the branch, by putting it in parentheses. And then continuing on, the next is another CH3 group. Okay, so that's how you work with the line angle, the condensed structural formula. With the line angle drawing, you just convert each of these carbons into a dot. So here's 1, 2, 3. Okay, and then there's a branch coming off that central carbon. So that's going to be the line angle drawing. And that's the isomer of butane. Okay, so looking at the next, we've got pentane. So pentane has the prefix pent, which means 5 carbons. Okay, the ANE is the same alkane family, all single bonds. So the chemical formula is going to be C5, and then we can figure out the number of hydrogens. So that would be 5 times 2 plus 2, so H12. Let's start with the fact that this is just pentane, not an isomer of pentane. So that's going to be the normal straight chain version. So this would be 5 carbons, 1, 2, 3, 4, 5. And then make sure every carbon has 4 bonds coming out of it, and that those bonds are going to hydrogens. So here's 1, here's 2, here's carbon 3, here's 4, and then the last carbon. Okay, so the condensed structural formula shows what's bonded to each carbon. And so this first group on the left is a carbon with 3 hydrogens. So that's CH3. And then all of these center carbons, here's CH2, here's another CH2, and here's another CH2. So there's 3 of those. So let's write those: CH2, CH2, and then CH2. Okay. And then the last carbon on the right in this structure is another CH3, a carbon with 3 hydrogens. So that's CH3. Now, another way you could do this is by combining those CH2 groups, there's 3 of them, and actually put those into parentheses. And so that you don't confuse it with a parentheses that has a branch, this has a subscript 3. So when that's a subscript 3, it means it's not a branch. Okay, because of that subscript. It means that you just have 3 of those in the parentheses. And that's these 3 in the condensed structural formula with the CH3. Okay, So then let's convert this to a line angle drawing. For pentane, it's going to be 1, 2, 3, 4, 5. Now, it doesn't matter if the zigzag is going down, up, up, or up, down, as long as you have 5, 1, 2, 3, 4, 5 total in the line angle drawing. So that's the ends of the line and then the vertices in the middle. Okay. Now for this next one, we are given the condensed structural formula. So from this condensed structural formula here, let's build the structure, moving this direction, building the structure. You have CH3. So that's a carbon with 3 hydrogens. And then this next is, let me do this one at a time. So I already did this one, CH3. The next is a CH with the parentheses CH3. So remember what that means. It means you have a carbon. Okay, so this is a carbon with a hydrogen. The hydrogen can be up or down. Okay, but what the parentheses means, it's a branch off that main chain. So this can be also up or down. But because the hydrogen was down, I put the CH3 up. If you had it flipped, the hydrogen up and the CH3 down, that's correct too. The next is, so next in green is another CH2, is a CH2 group. So that means that I'm going to add on to here a carbon with 2 hydrogens. So 1 up and 1 down, 2 hydrogens. And then in the condensed structural formula on the right is that final CH3 group, which means that on the structure, you're going to have a carbon with 3 hydrogens at the end. Okay, so when you add all these up, how many carbons and how many hydrogens? There's 1, 2, 3, 4, 5 carbons. So this is C5. And then when you add up all those hydrogens, you'll find that there's 12 of these, C5H12. So what do you have here? You have the same chemical formula as the above. So these are the same chemical formula, but you have a different structure. This structure that you just drew is different from this structure that we drew previously. So when you have the same chemical formula, but a different structure, that's an isomer. So this is an isomer of pentane or isopentane. Okay, and so the line angle drawing will also show that when you have 1, 2, 3, 4 carbons in the chain, and then there's a branch coming off that second carbon. So let me highlight that. This is a branch right here, the CH3 branch. So this is a branch coming off that second carbon. Okay, so let's take a look at this next condensed structural formula that we're given. So we can build the structure from that. This is going to be a CH3. So it's a carbon with 3 hydrogens. The next is CH. Let's underline that actually. So this is a CH and then a branch. That's what that parentheses means. And that branch is a little bit longer than we've dealt with. So let's draw this. This is a carbon with a hydrogen. I'm going to put the hydrogen above this time because it doesn't actually matter. And then that branch is CH2, CH3. You can just write all that out. And then the next is you have a CH3. So this is a carbon with 3 hydrogens. Okay. What you have here, though, is counting all of these carbons. You have 1, 2, 3, 4, 5 carbons. That's C5. And then if you count all those hydrogens, H12. So this also has the same chemical formula, C5H12, but a different structure. Okay, because that branch is different. So when you have a different structure, this is another isomer of pentane. So because they're both named isopentane, we have another naming, a better, more precise, more specific naming that we'll get to in the next worksheet. And so that's because of isomers. Once you have branching, you can have these isomers that are different, but you want to have different names. Okay, so this is going to be 1, 2 carbons, and then a branch that is 2 carbons long. And then you have another. So this is the branch here, which is 2 carbons long, is this branch here that's 2 carbons long. It can go up or down, and you could just draw that as a mirror image. And for this last one, you see you have what looks like a six member ring. So there's 1, 2, 3, 4, 5, 6 carbons in there. So that's not a hexagon. Okay, so that is a 6-member ring with carbons. Remember, that's what you're looking at now. And so what this is a ring version of the 6-member hexane. And that means it's called cyclohexane when you have all of that connected. And so let's draw this out. So if this is 6 carbons, 1, 2, 3, 4, 5, 6, each of those carbons has to have 4 bonds. So starting at the upper left, I can see there's already 2 bonds for every single one of those carbons. Every single one of the carbons in the ring has 2 bonds. And so that means that every carbon needs to have added to it 2 hydrogens. Okay, and so that is the full structure. The condensed structural formula is a CH2 group that's at every vertex in this hexagon. And this is called the cyclohexane when you have connected this together. Now, when you count up all those carbons, there's going to be 6 of them, but there's not the same calculation for the hydrogens. You actually have 2 less hydrogens than the n 2n plus 2, because you have these connected, the carbons are connected around in the ring. So instead of C6H14, it's C6H12 when you count up all those hydrogens. So that's what happens when you form the ring, is you lose 2 hydrogens. Okay. This is drawing or writing the chemical name for these organic molecules that have some branching going on. Or we'll see also if these molecules start to have different atoms in there. When they're not just carbon and hydrogen, you'll have what's called a functional group. Or when you have not just single bonds, when you have a double bond or triple bond, or when you have a branch, that leads to these variations in the names when the starting point is the alkane family names. So that's going back to here. The starting point of these alkane family names, you'll notice they all end in ane, okay? And we'll build from that. Also, as far as this worksheet, these functional groups here, we're gonna work on in the next lecture. So save this worksheet, you'll see it in next lecture. But let's go down to the rules for, or the steps for writing the chemical name when you're given a structure. Okay, so we looked at these 2 examples in the video. So these 2 examples, and you are starting with the longest continuous chain of carbon atoms. That's going to be the parent chain. Numbering the carbons in that parent chain, starting from the end that's closest to something going on. It's going to be a branch, a double bond, triple bond, or a functional group, which is having a different atom in there, not just carbon or hydrogen. Okay, so let's look at this first example here in this worksheet. So we're asked to write the chemical name. And this is the longest continuous chain of carbons is going to be this one going from left to right here. Okay, but how should we number this? So you can either number it from left to right going in this direction, or from right to left going in that direction. And the way you want to number this is by choosing the side that has something going on or closest to something going on. So that's this. What's going on here is a branch. This is a branch right here. And numbering this, you're going to choose left to right because you want the branch to have the lowest possible number. So in numbering this, you want to number this 1. This is carbon number 1. Here's number 2. Here's number 3, 4, and 5. The branch will then be on carbon 2, C2, because you chose this as carbon number 1 on the left side. If you had numbered it the other direction, this branch would be on carbon number 4. So you want the branch to have the lowest possible number. Okay, so going back up, I numbered the carbons on the parent chain, and then you want to name any branches by the location and the length. So the meaning of that is the location is the carbon number on that parent chain. And then the length is based on how many carbons there are. So using those prefixes meth, eth, prop, a meth means it's 1 carbon, an eth means it's 2 carbons, a prop is 3 carbons, a but is 4 carbons. And then a YL ending is always added to a branch name. So let's go down and look at this. So if you have the branch on carbon number 2, this carbon number 2 branch has the name is going to be the location number comes first. And so that's on carbon number 2, so the 2. And then it is a 1 carbon long branch. It's just CH3. So it's not very long, right? It's just 1 carbon, which is a 1 carbon branch. Has the name meth, right? Has the name meth. And then you have a YL ending for the branch name. Okay, so branches always have to end in YL. And this connection between the number and a letter has to be with a dash. Okay, so going back up here, that's what this says. Location is the carbon number. And then the name is based on the number of carbons with those prefixes. And then you add the YL ending. And then you connect the number to the letters using a dash. Okay, so for instance, I just wrote 2-ethyl, or 3-ethyl would be a 2 carbon branch located at carbon number 3. Okay, so step number 4 says if you have a branch more than once, you combine them using an appropriate prefix. We don't have more than 1 branch. But step number 5 we are going to get to is adding the parent name using those same prefixes. And so the parent name of this one, it's a 5 carbon parent chain. That's how long that chain is that we circled. So what's the 5 carbon parent chain prefix going to be? It would be pent. And they're all single bonds. There's no double bonds in there. There's no functional group. So the name ending when you have all single bonds is A-N-E, pentane. So that's what this says up here. When you have all single bonds, it's an A-N-E name ending of the parent name. Okay, we'll find some with double bonds, triple bonds. And so we now want to combine these two. So combining the branch with the parent name, it's going to be 2-methyl. The branch name comes first, and then the name of the parent, pentane. Okay, so you can just combine those letters. So letters are combined without a dash, but a number to a letter has to be combined with a dash. So that is combining the branch with the parent name, and that would be the name of this molecule. Okay. Now I'm not going to keep going back and forth on the instructions. So let's start with number 1 on this next example, which is finding the longest parent chain. The longest chain is this one, which is 4 carbons long. So this is a 4 carbon parent. And then you want to number this 4 carbon parent from where something's going on. So left to right or right to left. This is a double bond here. And you want that to have the lowest possible number. So I'm going to number this from left to right, 1, 2, 3, and 4. So that allows the double bond to be on carbon number 1. It's going from carbon number 1 to carbon number 2. Okay, but you give it the lowest number from the carbon it originates from. So the double bond is on carbon number 1. Okay, so we don't have any branches. So there's no branching going on. So when you have no branches, I don't have to name any branches. What you do then is you have the parent name, which is from 4 carbons, it's but. And instead of being an A-N-E name ending, the name ending is no longer A-N-E because you have this double bond. So for the double bond, you change the name ending from A-N-E to E-N-E. Okay, and you also have to add the location of that double bond at the front. So this would become the location of the double bond is 1, and this but we keep B-U-T and change the name ending to E-N-E. Now, because you can get rid of ones, this actually is normally just called butene without the 1. So you can put ones in, you could take ones out. That's true of chemical formulas and also true of chemical names. Okay, so this would also be the name 1-butene or butene without the 1. Okay, so the next example we're looking at is look for the longest continuous carbon chain. So that's just going straight across. So this is 1, 2, 3, 4, 5, 6 carbon parents, 6 carbons in this parent chain. And there's no branching going on. So that was easy to spot. But now you want to decide how to number this. And there's a double bond here. So this is a double bond, and you want to number this so that double bond has the lowest possible number. So this actually works going from left to right or right to left. That double bond will be on carbon number 3. So it's on carbon number 3 going to carbon number 4, whether you number it left to right or right to left. So what that means, though, is the 6 carbon parent would be named hexane. Okay, but because there's a double bond, we want to take off the A-N-E and change that name ending to the E-N-E to indicate the double bond. So this is going to be, instead of hexane, it's hexene. So it could be the 3 is the location of that double bond. So I add the location of the double bond at the front, 3, and then the name ending E-N-E. So this one is not a 1, and we don't get to get rid of the 3. You can only get rid of 1s. So the name of this molecule is 3-hexene. That's an X, H-E-X. Okay, and let's look at this next example. We've got to find the longest continuous chain. Now it's normally going to be just going straight across. So just going straight across, you've got this 3 carbons, and then this is a branch. So this is a branch off that main carbon chain. So this is a 3 carbon parent chain. And this is a branch that is 1 carbon long. So it's a 1 carbon long branch. It's not very long, right? Okay, so here's the process where you start with naming the branch. So the name of the branch is by numbering the carbons. You can either choose left to right or right to left, either one, 1, 2, 3. The branch is on carbon number 2. Okay, so the name of the branch starts with the location of the branch, which is carbon number 2. And then the length of the branch when it's 1 carbon is the prefix meth. When you have the branch, it always has to have the ending YL. So that's the name of the branch is 2-methyl. Okay, the 3 carbon parent is coming from the 3 carbon prefix. So meth eth prop is when you have 3 carbons. And when they're all single bonds, it's A-N-E. So now you want to combine those to have the name of the molecule. You take the name of the branch and you rewrite that at the front, 2-methyl, and then attach on the parent name, propane. And notice that the name which has a letter, methyl, and the number 2, when you have the connection of a number to a letter, you have to have a dash. So 2-methylpropane is the name of this molecule. Okay, let's take a look at this next one. So the next one, you've got 4 carbons in this continuous line. So this is a 4 carbon parent. And that 4 carbon parent does not have any branching. but you do have a triple bond. That's what this is. It's a triple bond in there. And to give it the lowest possible number, we're going to number this starting from that triple bond. So 1, 2, 3, and 4. So the triple bond originates from carbon number 1 and goes to carbon number 2. And technically, you would write it that it's on carbon number 1. Okay. So what that means is we need the name of the 4-carbon parent. So the prefix when you have 4 carbons is methylpropute. It would be called butane, but because of the triple bond, you don't keep that name ending anymore. So the triple bond means you change the name ending. And we haven't seen the name ending for the triple bond yet. So let me pull this back. When you have a double bond, the name ending is ENE. When you have a triple bond, the name ending becomes YNE, and you also have to add the location of that bond to the front of the name. Okay, so let's remember that the name ending for the triple bond is YNE. And so that I'm going to change the name ending to the YNE and add the location to the front. So this name is going to be a 1 and then butane, TYNE. Because we can get rid of ones, this one we could just call butane. So those are 2 possible names. Okay, now let's take a look at this last molecule. So here, this is a kind of a modified condensed structural formula, but you want to make sure you find the longest continuous chain, which sometimes goes up into a branch. So this is 1, 2, 3, 4, 5 going across, but let's check and make sure 1, 2, 3, 4, 5 is also a possibility going up. And so whether you call it straight across like this or going up, it's 5 carbons is the longest continuous chain. So there's a 5-carbon parent. So you could have numbered it straight across or up into the branch, and 5 carbons would be the longest. Okay, so what that means is that there are 2 branches. So let's change to red. So this is a branch. So this is a 1-carbon long branch, not very long. And this is a 2-carbon long branch. I'll write it out. 2-carbon long branch. So we have 2 branches there. So we want to number this so that the branches have the lowest possible numbers. So that's going to be numbering from left to right. 1, 2, 3, 4, and 5. So the branch name, the name of this 1-carbon branch is going to be location first. So that's 2. And then dash for a 1-carbon long, you use the prefix meth, and then that's a YL. The name of this 2-carbon branch is the location has to be first. So it's coming off carbon number 3. And then the 2-carbon length is the prefix F. Okay. And then the branch name is always going to end in a YL. Now the 5-carbon parent is going to be the prefix pent. They're all single bond, so it's ANE. So when you have branches, you combine all these. So combined, you would write this 2-methyl 3-ethyl. Now, why all those dashes? Because when you have a letter and a number, you have to connect those using a dash. But when you have letters connected, you don't need a dash. Okay. Or another way to write this is in alphabetical order is actually more correct. 3-ethyl, 2-methyl, and then pentane. Okay, and so that's what this says up here is that when you have these branches, they have to be listed in alphabetical order. Okay, so that is these branches here. The ethyl came before the methyl, okay, instead of the numbers. Okay, so how do you guys feel about that? The process of naming is basically naming the sections of each part of an organic molecule and then putting all those sections together. And so we'll see this is how you can get a very long name of an organic molecule. And we'll see that in the names of drugs. So this time we are given the name and basically interpreting all those parts so we can build the structure. And so given this name, 2-butene, all the parts, you want to start from the right side, which is, look at this ENE, which means it's a double bond. There's a double bond. And when you have a double bond or triple bond indicated by the name ending, the ENE here is double bond, the location has to be a number at the front. Okay, so that number at the front, that 2, means that that double bond is on carbon number 2. Okay, then another part of this is the but. So you got, basically you're looking at all the parts and what do they mean? So the but means that this is a 4-carbon parent chain. Okay, so once you have identified what all the parts, what every letter and every number represent in the name, then you build it based on basically what you just wrote. So you have a 4-carbon parent. So first the 4-carbon parent, 1, 2, 3, 4, and then number it. So as I mentioned, you get to number it 1, 2, 3, 4, left to right, because you're building it. When you add the double bond on carbon number 2, this is going from carbon number 2. This is carbon number 2 to the next carbon, and it has to be the next carbon up. So you can't go from 2 to 1. It's going from 2 to 3, because if you draw it from 2 to 1, then it would have been the double bond on carbon number 1. So the double bond is numbered given the lower number where it originates from. Okay, so once you've done that, 4-carbon parent, add the double bond, there's no other parts of that name, then you add hydrogens to fill in the rest, making sure that every carbon has 4 bonds coming out of it. So this is adding 3 more, 1, 2, 3. This carbon here, number 2, already has 3 bonds, so you only need 1 more. This carbon number 3 already has 3 bonds, so you only need 1 more. And then both of those hydrogens could be up or down, doesn't matter. And then this carbon number 4 needs 3 more. So that's that structure for 2-butene. For the next one, we have propene is the name. So start at the right side of the name and look at this name ending. So ENE means there's a double bond. When you have a double bond or a triple bond, you need to look at the front of it to find the location. If there's no location, it must mean the default, which is on carbon number 1. Okay, so when there's no location, it must mean that there was a 1 in there that was taken away. Okay, and then the next part is prop. So what does prop indicate? So prop is the prefix that is 3 carbons. That's a 3-carbon parent. Okay, so remember, you always have this. I'm going to go back up to here. Sorry to make you dizzy. You always have this for your prefixes of those alkane names in case you're trying to remember what are those meth, eth, prop. Okay, so I've got going back. The 3-carbon parent, we're going to build 1, 2, 3, and then number these carbons 1, 2, 3, and then add a double bond on carbon number 1. So that's from carbon number 1 going to carbon number 2 is a double bond. That's it for the instructions. So then add hydrogens to fill in the rest. So I'm 2 more hydrogens on carbon 1. Carbon number 2 has 3 already, so add 1 more hydrogen, and carbon number 3, I'm going to need to add 3. Okay. All right, so the next example is ethine. Okay, so starting from the right side of the name, there's a YNE. So that YNE name ending means that there's a triple bond. And if you have a double bond or triple bond, you got to look back at the name. At the front of the name, there should be a location number. If there's no location number, then that must be the default, which is carbon number 1, because there was a 1 removed. Eth is the next part. So that eth means that there's a 2-carbon parent. Okay, so building this with a 2-carbon parent have 2 carbons. Number those 2 carbons 1 and 2. And then put a triple bond coming from carbon number 1. So this is from 1 to 2 triple bond. So covered all that from the name. So that means add hydrogens to fill in the rest. So when there's already 3 bonds, you only need 1 more hydrogen. It can be left, down, up, right, as long as you just have 1 hydrogen. Okay. So let's take a look at these last 2 here. Well, there's last 3 actually. So starting from the right, you have ANE, which is all single bonds. Okay, so that's what ANE means, all single bonds. And then pent is a 5-carbon parent with all single bonds. YL means that you have a branch. And meth means that it is 1 carbon long. And then di means that there's actually two of these branches. That's what the di means. And the 3 and the 3 are the locations. So they are at carbon number 3 and also carbon number 3. That's what the 3 and the 3 mean. Okay, so that's combining that. So they are 2 branches that are each 1 carbon long and located at carbon number 3 and carbon number 3. And they are on a 5-carbon parent chain. So let's build this. 1, 2, 3, 4, 5. And then number those carbons. 1, 2, 3, 4, and 5. Add. Okay, those are all single bonds. So next you want to add those branches. So there are 2 branches. One is on carbon number 3. And it's 1 carbon long, so that's CH3. Another branch is also on carbon number 3, and it's also 1 carbon long, so that's CH3. Now you might ask me again, how did I know there were 2 branches? That's because what I snuck in there was this di. That means 2 branches. Okay, so this is also the hint was that there's 2 location numbers. When there's 2 location numbers, that means you got more than one thing. But we got the single bonds, this parent chain, the branches, each 1 carbon long, there are 2 of them. That's everything on here. So now you fill in the rest with hydrogens. So then make sure that every carbon has 4 bonds. Put hydrogens on those carbons. And that would be the structure of 3,3-dimethylpentane. Now for 2,3-dimethylpentane, this is almost the same. So you still have the 5-carbon parent. That's what pentane is. You have the 5-carbon parent with all single bonds. And then you also have 2 branches. The di means 2. Meth means 1. So it's a 1 carbon long branch. And you know it's a branch because it's the YL. But the locations are on, this time, carbon number 2. That's what the 2 is. And then the comma 3 is the other location. So the locations are on carbon 2 and on carbon 3. So building this, you still start the same. 1, 2, 3, 4, 5 carbons. Number those carbons. 1, 2, 3, 4, and 5. And then you have those 1 carbon long branches. So this is on carbon number 2, CH3, and on carbon number 3, CH3. So carbon number 2 and carbon number 3 have the 1 carbon branch, which is a CH3. So that is a little bit different, which is why the names are different and you have structures are different. So those are isomers, and now they're not the exact same name. They're not just isomers of pentane. Okay, finish this out by making sure every carbon has 4 bonds coming out of it, and that those are going to hydrogens. Okay, and then let's go to the last one, which is N-butyne. So the name ending is YNE. and a YNE means it's a triple bond. When you have a double bond or triple bond, you look to the front of the name for a location number. And since there's no location number at the front of the name, there's just an N, it means must be on carbon 1 is the default if there's no number. Bute means that there's a 4-carbon parent. And then what does that N mean? So the N means normal or straight chain. We looked at that at the very beginning in talking about the isomers. Okay, so that will not really affect the structure here. So in building this, we need a 4-carbon parent chain. So 1, 2, 3, 4, and then number those carbons 1, 2, 3, and 4. Okay, now we want to have a triple bond on carbon number 1. So make that a triple bond. And so it's all straight chain, normal, no branching. That means no branching. That's what the N means. And then there's 4-carbon parent, got that. And the triple bond on carbon number 1. So once you've satisfied all that, make sure every carbon has 4 bonds coming out of it. And add hydrogens to the ends of those. Okay, so that is a little bit, this happens when I get to the bottom, but that is the structure of N-butene.
Does C2